Good afternoon, everyone. Welcome to the jointing webinar. There's still some people signing on, but we're going to go ahead and start with some of the logistics and introductions. And today was supposed to be a face-to-face jointing workshop. However, we're happy that we can meet you all here online and share some information with you. We decided, an all day long online session would be a bit, wouldn't be productive. So we did a combination of a short webinar with making some additional resources available to you that you can do at your convenience. So if you have not completed some of those other recordings prior to this, you will still have access to that following this webinar. So welcome everyone, and let's see, where's why is it not letting me? There we go. So my name's Amy Wadle, and I'm the Director of Concrete Pavements with Florida Concrete and Products Association. We are the industry association for cement, aggregate, ready-mix concrete, as well as concrete pavement companies across the state of Florida. And additionally, we want to thank our members for their support and making these educational programs possible. So today, additionally, Florida Concrete Products Association is the Florida chapter of the American Concrete Pavement Association, and that is who we have partnered with today to bring you this webinar. We have two instructors today. Eric Ferrebee is the Director of Technical Services with the American Concrete Pavement Association. Eric joined the ACPA staff in 2014. He has a bachelor's and master's degree from the University of Illinois. Something happened to my slideshow here. Sorry about that. And Eric has been instrumental in providing technical support and consulting services to ACPA members and agencies. He has been developing ACPA's WikiPave online technical resources, where we source some of the additional resources we're making available to you today. He also has helped to develop pavementdesigner.org. If you are not familiar with that, that is a new web-based free online concrete pavement design tool. He also supports, Eric also supports the association's mission through development of technical literature, overseeing research projects, and enhancing concrete pavement technology transfer and information sharing. We also have Mark Snyder, who is the President and Manager of Pavement Engineering and Research Consultants. He has a bachelor's, master's, and doctorate degree also from the University of Illinois, specializing in structures and pavement engineering with emphasis on concrete pavement design, rehabilitation, and materials topics. He has more than 35 years of experience in these fields, including 13 years as professor of civil engineering and 10 years working for the concrete paving industry before working full-time as an engineering consultant. So we're very pleased today to have both Mark and Eric with us and providing this content. They're going to present some information, and then we're going to have time for questions at the end. You should have, and it's a little different on different people's screens, but the ability, to send in the chat questions. So please send in your questions as we go through this. And I'm going to turn it over now to Eric to start the presentation. Thank you, Eric.
Thank you, Amy. So as I get my slides up here, let's see here. There we go. Okay, so today Mark and I are going to go through a brief introduction into joint design, layout, and construction. But we recognize that really we're trying to kind of give you an introduction into basically a full day workshop here in the next hour or so. And so that's why we really provided those, let's see here, my slides will work, provided those jointing resources. Now, if you haven't taken a look at those, like Amy mentioned, we really encourage you to take a look at those, because that's really where all of the content that we're talking about today was kind of developed from. It goes into a lot more detail on all of those, all of the topics that we're talking about today. So really encourage you to take a look at those. They're all available for free with the links provided. So with that, we'll jump right in and talk a little bit about why we joint concrete. Why do we joint concrete pavements? And so the biggest reason, the one that's most prevalent and the one that comes to mind most often, is the concrete shrinks. So when we place concrete through a few different mechanisms, whether it be drying shrinkage, thermal shrinkage, or chemical shrinkage, the concrete wants to shrink. And shrinkage itself is not the problem. So if we had our fresh concrete or hot, moist concrete, as it begins to cure and harden, what we see is that it wants to shrink. Now, if we were placing concrete on something that was frictionless, wouldn't be a problem, but we place our concrete pavements on a subgrade and a subbase, and that provides restraint. And that restraint wants to stop the pavement from shrinking. And so as that restraint develops, or as that restraint builds, it builds stresses within our pavement, and the concrete wants to crack to relieve that stress. And so if we didn't do any type of jointing, what would happen is over time we would get a crack every about 40 to 80 feet in a transverse direction. And then that would progress down to about every 15 to 20 feet over time. And so since cracks are not very, are things that we see and we think that our pavement has failed, when really they're just a natural thing that happens, we want to provide a place for that crack to happen that's easier to maintain. And that's one of the biggest reasons why we joint our pavements. Now, some of the other reasons we joint our concrete pavements, we want to be able to divide these pavements into constructible lanes. As you can imagine, if we were paving, say, 48 feet wide or 50 feet wide, whatever, it's hard to find a paving machine that would be able to do something that wide in one pass. And so we have to be able to construct these pavements. So we would want to pave 2 lanes at a time and then come back in and put a shoulder on. We would likely have to do that in multiple passes. And so we have to divide the pavement into construction lanes and increments. Additionally, we have to accommodate slab movements. Once those cracks actually initiate, the slab is going to continue to expand and contract through the life of the pavement. That's going to happen with thermal cycles, moisture cycles. It's going to keep expanding and contracting, and that's normal. Additionally, with those slabs, they're going to curl and warp. We're going to talk a little bit about that in just a few minutes. And so we got to accommodate how that's happening and kind of decrease the stresses associated with those as well. Additionally, we have to be able to know where to put load transfer devices. If we're going to have significant truck traffic, we want to have a smooth pavement. We're likely going to need dowel bars within our pavement. Mark's going to talk a little bit about dowel bars in a little bit, but we need to know where those go. And so that's why we have to know where those joints are placed, so we know where to put our dowel bars as well. And if we're sealing our joints, we have to know where that seal needs to go, so we have to have that joint, provide that sealant reservoir for the sealant as well. So one common misconception is that the joints are for lane delineation, meaning the joints line up with our lane lines. And that doesn't always have to be the case. You can see here a great example from Iowa where those joints are actually placed in the center of the lane. And you can see as a truck would be driving here, it would be straddling that joint. And that just happens to work out sometimes when we're paving these sections and our shoulders are a certain width. You can see that it works well for this situation. Additionally, it's something that we've really taken into account, especially with concrete overlays where we're doing thinner sections with smaller joint spacings. And so while it oftentimes happens where our longitudinal joints are right where our lane lines would be, it doesn't always have to be the case. Okay, so let's talk about the different types of joints that we have within our concrete pavement. So the main types of joints that we'll see that make up about 95 to 98% of our concrete pavement joints are our contraction joints, our construction joints, and our isolation joints. So those three types of joints are really what make up most of our concrete pavement joints. Now all of those can happen in the transverse and longitudinal direction, and we'll see those in just a minute. But they are very important, and considering them is also important as well. We also have some specialty joints, which are mainly transitions from concrete to asphalt, or concrete to a bridge, or a terminal joint when we're getting to the end of a concrete section. So we'll talk about each of these fairly briefly. So first are our contraction joints. And our contraction joints in the transverse direction are typical sawed joints. We're going through paving a long tangent section. We have to saw in our transverse joints to cut down to that about 15-foot joint spacing range. And so these can either be, as you can see here, they can be doweled or they can be undoweled where we have aggregate interlock. So the dowel is going to provide long-term load transfer. Aggregate interlock may be okay if we don't have a whole lot of truck traffic. Similarly, we can have a contraction joint or a sawed joint in a longitudinal direction as well. If we're paving, say, 24 feet wide, we would likely want to cut that down to about 12 feet wide. So we would saw a joint in there, a longitudinal contraction joint. And so these can have a tie bar or they can be untied, as you can see here. Okay. The next type of joint is our construction joint. You can see a few different examples of these, but our construction joints are typically have a flat face to them. And there are a few different ways that we can do this. So our construction joints are almost always going to have a dowel bar in there because we don't have aggregate interlock to transfer load from one slab to the next. And so we almost always have a dowel bar to have that mechanical load transfer device within our pavement. Occasionally, you'll see a tie bar section in there, but a lot more often we'll see a doweled section or a dowel bar at these types of joints. So there are a number of different ways we can do these header sections or these transverse construction joints. You can see here where we're doing a fair bit of handwork, where we're actually doing a formed header. You can see here we've already got our dowel bars in place, and they're actually doing a lot of handwork to get that formed header going. Now, these are going to happen at the end of a day's placement, where we're finishing off for a day, and we're going to start the next day's paving right there, right at that header. So there, you can see here what a formed header looks like. And so for a formed header, there are a few different ways you can do the dowel bars. You can have them already in place, as we saw there, or we can have dummy dowels within there, or false dowels, where we would slide the dowel bar into a slot that's created already to make sure that we have good consolidation around that dowel bar. And so this usually requires a fair bit of handwork as well. The other type of header that we can have is a sawed header. And so this is where if we had a paving machine, we would pave through a head of concrete, which we can see here on the left photo. And then we would come back in and saw that whole section off, and then we would remove this section of concrete. And after we do that, we would have to come back in and drill in and epoxy our dowel bars such that they're fully encased in that section, so we can provide load transfer. You can see here in this section, they've actually put a mat down so they can actually get this section of concrete off fairly easily. The key to getting these to perform well is to make sure that these dowel bars are well positioned, make sure they're aligned fairly well, and make sure they're as fully encased in that epoxy or that grout as we possibly can to make sure they're well installed. Now, when we resume paving at these transverse construction joints or headers, we want to make sure that we wait at least 6 hours, make sure it has the time to, that existing section has some time to set. We're ready to start on the other side. We will have some handwork to do when we start that section up and make sure we get some good vibration so we consolidate our concrete on that leave end of that construction joint. So it takes a little bit of work, but they do perform pretty well. So our next type of joint is our longitudinal construction joint. And so these types of joints happen in between paving lanes. So we pave one section of concrete, and then we have to come in and pave the section just adjacent to it. Most often, we're going to see that these sections will be tied together with a tie bar. The tie bar is really just there to make sure that joint doesn't open up and keep these two sections of concrete together. So we have that tie bar in there to keep that joint tight. So here's a good shot of what we can see, where we can see just about every type of joint. You can see the longitudinal contraction joints, the saw joints, which are coming in between here in these paving lanes where they're sawed in here. Our transverse contraction joints or saw joints would be coming along in here. You can see a few of them as we go through this paving operation. And then you can see our longitudinal construction joints that are happening in between these paving lanes. So you can see a lot of those different operations here in this industrial site. Great overview. Now, one thing with our longitudinal construction joints that I always like to mention is the use of keyways. So keyways are this idea where we have one section of concrete, in a paving lane that fits into another and kind of provides a smooth load transfer from one section to the next. However, with these conventional keyways, we've seen it's a relatively high risk of bad construction where you can see it can be kind of hard to consolidate that concrete in those sections that kind of jut out a little bit. It can happen on both sides of that keyway. And so we don't really recommend this conventional type of keyway much anymore. Additionally, even if it is constructed properly, we can see that this section here and this section here can actually shear off, and then you get a little gap in between your two sections of concrete. So we don't really recommend this type of keyway anymore. There is a new type of keyway that's more of a sinusoidal section, but it hasn't really caught on in the US. So just a mention of that. Our last type of joint is an isolation joint. And an isolation joint is exactly what it sounds like. We're trying to isolate one section from another. And we can do that a few different ways. We have a sleeper slab section, we have a thickened edge section, and then we have a doweled isolation, or in this case, it could be called an expansion joint. So the idea is to make sure that one section of concrete is not influencing another, or if we're paving up against a structure or say any type of drainage facility, this will make sure that those two don't interact either in a horizontal or in a vertical direction. Make sure that we're not influencing our pavement, and our pavement isn't influencing that structure. You can see what that isolation joint looks like over here. It's just usually about a quarter-inch or quarter-inch, half-inch filler board to isolate the two sections. Now, most often when we talk about isolation joints, we're not talking about the same thing as an expansion joint. Expansion joints are really more used on bridge sections. So there is a document that talks about the differences between isolation and expansion joints and when they're appropriate. That's another free resource as well. So our last types of joints are those specialty joints. Really the main ones that you would encounter are the transitions from concrete to asphalt, and you can see what a few of those look like here. Most often we're going to use some sort of thickened edge to kind of firm up that free edge of concrete and reduce the stresses there and make sure that we get a smooth transition from our concrete to our asphalt. You can see a few different options for that. Here we've actually got the concrete extending underneath the asphalt with a dowel bar there to help transfer the load and have that smooth transition from concrete to asphalt. If we do it well and construct it well, we can get a nice transition from that asphalt to the concrete section that can last a long time. Okay, so that's a little bit on our types of joints. Next thing that we got to talk about real quick is our panel length, our aspect ratio. What's that maximum joint spacing that we want to think about when we start getting into our joint layout for our concrete pavement? When we start thinking about maximum joint spacing, the thing that we always kind of want to consider in the back of our head is curling and warping, because these slabs are going to have that curling and warping stress from the moisture, from the heat. All of that's going to influence the stresses in our pavement. And so we can kind of control that when we control the size of the slabs that we have. And so by reducing the size of our slabs, we can reduce those stresses and control how they're going to impact our pavement's performance. You can see here a good kind of introduction of what happens when we start cutting our panels in half, basically. And this is something that we do a lot more in concrete overlays, where we go to, say, shorter and shorter joint spacing down all the way to 6-foot panels. But really the idea is kind of consistent, that if we can control the size of our slab, we can control these curling and warping stresses. And then we can also see how the loading scenario actually influences that as well. Because you can see here what a truck would look like going onto, say, a 15 or 18-foot panel, where we've got that drive axle along with that first tandem axle on one slab. You can see, add that together with our curling and warping stresses, it's going to increase the stresses. So on overlays, when we cut these slabs shorter and shorter, and we have, say, 6-foot by 6-foot joint spacings, you can see we get one load on each slab. Can perform pretty well. We see it work really well on overlays. In some countries in the world, they actually use this on new construction as well. But to kind of illustrate this point that we can control the stresses within our concrete based on the joints, on the length of our joints, you can see here's kind of an output plot from Pavement ME, which is a pavement design software. You can see that if we go from, say, 20-foot joint spacings to 18-foot joint spacings to 17 down to 15-foot joint spacings for our transverse joints, we can significantly reduce the percent slabs cracked, the predicted percent slabs cracked. So that's one of the biggest ways that we control the stresses and the cracking within our pavement, by controlling the joint spacing of our concrete. And so we want to consider that when we're thinking about what should our joint spacing actually be. Pavement ME, or Mechanistic Empirical Pavement Design Guide, is a great tool for seeing how that influences pavement performance over time. So now if you're not designing the pavement, if you're just considering what should my joint spacing be based on, you know, the given thickness that your pavement section is, you can basically estimate a maximum joint spacing through this equation here, where we have our maximum joint spacing equals the thickness times a support constant. And so we figure out what type of support constant we need, whether we have an unstabilized subgrade or a stabilized subgrade, multiply it times our thickness. That's going to be our maximum joint spacing. We're going to cap that at 15 feet. We don't really want to go beyond 15-foot joint spacings. Should be illustrated by that graph that we just saw a couple slides ago. Additionally, we want to maintain an aspect ratio less than 1.5, which means that if we had a 12-foot wide slab, we definitely wouldn't want to go beyond 18 feet in the transverse direction. And so considering that, if we had a thinner slab, say 10-foot wide, we wouldn't want to go beyond 15 feet. So keep that in mind, especially as we go through joint layout for intersections where we may get some odd shaped panels in there. Now there is an app for that equation. If you don't want to remember the support constants, this is a free tool from ACPA. You can find it on apps.acpa.org. It's the maximum joint spacing calculator. You basically just provide your thickness of your concrete and then choose what type of support system you have underneath the concrete. It'll give you your maximum joint spacing, recommended maximum joint spacing. Now another way to do this that's been used before is by considering the ratio of the maximum joint spacing to the radius of relative stiffness, which is kind of defining your slab foundation. And so by limiting this ratio of joint spacing to radius of relative stiffness, you kind of come up with similar numbers, but it's a little more mechanistic than that empirical approach that we saw on the previous slide. And there's another tool that can help with this as well. It's the radius of relative stiffness calculator. It'll calculate this bottom L for you, and then you can calculate your big L or maximum joint spacing based off of these relationships. All right. So now that we know our types of joints and a little bit on our aspect ratio and kind of our layout considerations, we can go into joint layout for intersections. Now, this is where we spend a lot of our time talking when we're thinking about jointing concrete pavements, because our geometries start to get a little funky and we have some odd shaped panels that we have to deal with as best we can. And so that's what we're going to try to do here in the next 10 minutes. So the things to consider for intersections, what we want to consider is the thickness of both of the roadways as we approach. We'll see that in just a second. We want to consider the jointing, the spacing, which we just talked about with our aspect ratio and our maximum joint spacing. We want to consider the layout, which is what this methodology is really built for. But we also want to consider the maintaining traffic. We're going to phase this intersection and try to maintain traffic and construct the intersection under traffic. We need to consider that up front as designers such that it's actually constructible. And then there are a few other considerations as well. So when we're thinking about thickness, the biggest thing to think about is the physical and functional areas of the intersection. As you can imagine, we have got 2 roadways worth of traffic. So here we're going to see an increased amount of increased volume of traffic relative to either of the roadways. So one of the considerations is, do we need to thicken up the section of concrete to accommodate that extra traffic? And so here are a few simple guidelines to address that. So if we have 2 roadways with low traffic, we likely just take the thicker of the 2 roadways. If we have one roadway with low truck traffic and one roadway with high truck traffic, we would take, again, the thicker of the 2 sections. But if we have two sections or two roadways with high truck traffic, there we may want to add a 1/2 inch to an extra inch of concrete within that functional area to accommodate that additional, the additional truck traffic that we're seeing within, within that intersection. Okay, so now when we're laying out our joints and we're thinking about joint spacing, our best practices, the 5 things that we always want to kind of consider as we're going through this 10-step process is keep it short. We want to keep our panels roughly shorter. Again, that'll help reduce the stresses within our slabs. We want to keep them as uniform as possible. We don't want to have we don't want to have so many different geometries that it becomes hard to construct. We want to keep it perpendicular and roughly as square as possible. We want to keep this layout simple and practical for the contractor as well, because they actually have to build this section of concrete as well. So as we're going through and we're actually doing these intersections, a few more things to think about. We want to match any existing joints and cracks with this in location and type. So if we're coming in here and we paved a section of concrete and we're adding on a section to an existing pavement, we would want to match, say, an isolation joint with an isolation joint, have it at the same location. Additionally, if that existing pavement has any cracks within it, we would likely want to match it with a joint there, because if we didn't, we would have sympathy cracking here into our new pavement. So we're matching our joints in location and type, and matching cracks as well. Cutting joints at the proper time and depth gets into the construction of these things. It's a little more detailed on that side. We also want to match in, we want to place our joints to meet in pavement structures, and we'll see that when we get close to the end of the 10-step method. Consider that maximum joint spacing that we just talked about. We'll talk about isolation joints as well. And then one thing as designers we need to be cognizant of is that when we do a joint layout in the office, what we see on our plans may be different than what's actually out there in the field. And so we have to understand and communicate with the contractor how those plans may need to change when they are presented with something in the field that's different. And so that's where good communication really comes into play as well. Some things to avoid when we're going through and doing joint layout. We want to avoid odd-shaped panels, any panel that's too big or too small. You can see slabs less than 2 feet or greater than 15 feet. We really want to try to avoid those as much as possible. We want to keep things as square as possible, and if we can't keep it square, we want to keep the angles greater than 60 degrees. Anything less than 30 degrees, and you can see here, we're likely going to get a crack. That's what we're seeing at that top right photo. We want to minimize the creation of interior corners. We also want to minimize odd shapes and really large panels. Keep it square as possible. You can see here with that second photo, we've got an odd, wide-shaped panel, got a nice little crack in there. You can see a very similar section where they added a joint basically right where that crack happened, and we can reduce the risk of a random crack happening like that. All right, so we've got some rules for joint layout. Let's actually go through joint and intersection using this 10-step method. So we'll step by step go through this 10-step method. I'm going to go through this fairly quickly, but one of those free resources is focused solely on this 10-step method. So I'd encourage you to download that if you're looking to do a joint layout for an intersection. Okay, so our 10-step method for intersection starts with drawing all pavement edge and back of curb lines. So we start off with our bird's eye view of our pavement. Step 2, we lightly draw circumference return, taper return, and crossroad return lines. You can see we're basically offsetting our return lines from our edges of our pavement. This is going to reduce those sharp corners that we would see if we didn't follow this methodology. So step 3, we draw all lane lines on the main line and crossroad. We're not extending through our return lines yet. You can see we're stopping when we hit those return lines, but you can see we're starting to see what our joint layout may look like. If we have a skewed intersection, that crossroad return line is really the only one that we're crossing, but we're crossing it such that we are perpendicular with our direction of travel on our crossroad. So step 4, we start thinking like a contractor. So we would think, how would a contractor actually get in here and maybe use a slip form paver to pave these sections? And this can actually increase the productivity for the contractor and can also reduce the cost of this intersection. Now, it may not be the way a contractor would construct it, but it's a good way to consider how this section would be paved. So step 5, we start adding our transverse joints. And the first transverse joints we're going to place are the ones at any pavement width change. So anywhere where our pavement width is changing, you can see we're adding a transverse joint. So anywhere at the edges of those circumference or turn lines, we're adding transverse joints, even if they don't match up, as you can see here and here. And you can see here when we have any kink for, say, a right turn lane, we're adding transverse joints. So anywhere where our pavement width is changing, we're adding transverse joints. So step 6, we start adding the transverse joints outside of the center portion of our intersection. Again, here we're considering our maximum joint spacing, trying to keep this as uniform as possible. So you can see here, if this distance is greater than our maximum joint spacing, we're adding a joint, trying to keep things as uniform as possible. So step 7, we start to get into the inner portion of our intersection, laying out our joints in the form of an intersection box. And so we're actually defining this box by extending our edge of pavement lines into the intersection. We're still not crossing our taper and circumference or turn lines. That's where we're stopping this intersection box. You can see we're just about done with our joint layout. So step 8, we check the distance between our intersection box and our next transverse joint. If it's greater than our maximum joint spacing, we need to add a couple more joints. And that's what we'll see in step 9, where we add that transverse joint. You can see here on the north and south sections of this intersection, we didn't need that extra joint. On the east and west, we did need an extra joint between the intersection box and the other transverse joints. So you can see here our joint layout's looking pretty good. The last step, we have to deal with some cleanup and deal with those odd-shaped panels. Notice that this whole 10-step method is really getting those odd-shaped panels out of the center portion of the intersection and trying to minimize their impact on the design as much as possible. So you can see a few different ways of doing that. We have these details blown up a little bit as well on what they should actually look like to kind of improve performance as best as possible, how to deal with incorporating that into the curb and gutter section as well. So a few different details that are really helpful in this type of design. So a couple details that I do want to mention. When we have some of these sections, we may run into a scenario where we have a dead end joint. You can see what that looks like here, where we have a longitudinal joint that kind of just stops. And that has to happen because otherwise we would have a really small, sharp panel that would likely crack. And so if we have a dead end joint, there are a few different ways we can deal with that. We can either put rebar in that rebar where that joint stops. That makes sure that if we get a sympathy crack into this next panel, that crack remains tight and doesn't propagate. Or we can put a core hole at the end of that joint, and that'll make sure it doesn't propagate into the next slab as well. So if we do that core hole or that formed hole option, this is what it would look like in construction. And after construction, you can see what that looks like, where we have this hole, which would be backfilled with any type of repair material that we would use. And you can see that that'll make sure that we don't get that joint propagating into the next slab. So last thing that we really want to consider is our utilities and our drainage sections as well. So you can see here, we need to adjust our joint layout for those utilities that are in our pavement. You can see we want to adjust our joints to meet those objects with a joint. If we don't do that, we can run into some issues. So we have box outs in here. See what some of those look like with optional reinforcement. If we have a telescoping manhole, that's the one thing that we don't need to isolate from and adjust our joint layout for. That'll perform just fine. But if we have a drainage inlet, you can see adjusting those joints just a little bit will definitely improve our performance. And so a few different box out featured fixture details. You can see here what some of those will look like. A lot of times we're isolating around those structures, and this will help performance of our pavement. So if we do it correctly, you can see what that looks like. If we box out appropriately, these are fairly old pavements and old pictures, and you can see our performance is great. We don't see any cracking. If we don't box out properly, you can see here we can get some significant cracking that can deteriorate our pavement fairly quickly. In a lot of these situations, if we had just considered it in our jointing plan, say adjusted this joint to meet that manhole, we would see a lot better performance than what we see here. So where there's a will, there's a way. You can see that we may end up with some weird looking things, but you can see here, we're not cracking. We just have some odd joints laid out, and it performs pretty well. So good practice on the contractor side, especially when we get into those curved sections, laying out a stake and actually providing something for our sawing crew to actually saw those joints to. We'll make sure that we get those joints laid out where we want them to be. The last thing that I want to mention is the isolation joints. Isolation joints a lot of times are used when we have a T-type intersection or a skewed type intersection. And this is just going to make sure that this section of concrete does not push into the central portion of our intersection, building up stresses. There's more detail on that in the resources provided. The guide to intersections really goes through a lot of this as well. And when we're laying out these joints, this is kind of what a contractor is going through as well to determine what their bid price would be for doing all of this work as well. So it's something that's helpful for them as well. Now, this 10-step method works for different facilities as well. You can see here's a rest stop, and this would be a tolling plaza, and it works pretty well for those types of facilities, but we do have additional guidance for roundabouts and diverging diamond interchanges. So those are available as well. And so with that, I'd like to remind you that if you have any questions, please type those into the chat box and we will answer them at the end of the section. And for now, I'm going to send things over to Mark Snyder and he will carry on with a little more detail. Alrighty, so Mark, you should be the host now and you can take over and unmute yourself and present your stuff as soon as I stop sharing. There we go.
Okay, thank you, Eric. I'm going to carry on where he left off. He's talked all about laying out these joints. Let's talk a little bit about what goes into them besides the joint themselves, some of the steel that goes in there and the placement of that steel and the alignment of it and so on and so forth, as well as some of the construction aspects that Eric hadn't previously covered. So we'll start out talking about dowel load transfer system design considerations. Dowel bars, of course, are a very critical structural component of jointed concrete pavement. These are the smooth surfaced steel bars, typically steel bars, sometimes other materials as well, but typically steel bars, and they are smooth surfaced, so they allow the joints to open and close in response to temperature and moisture changes, and thereby preventing uncontrolled cracking from taking place in the panels at places where we have not cut joints. Also, very importantly, they provide load transfer. They carry the load from one slab into the next. And in doing so, they reduce the deflections of the slabs. And if you reduce the slab deflections, then you also reduce the potential for erosion of support, erosion of the base layer or the sub-base layer or the foundation material. If you reduce the slab deflections, you also reduce the slab stresses. So we share the load across the joint. Only a fraction of the load is carried by each side, each panel on either side of the joint, and therefore you have only a fraction of the stresses on either side. They also serve to provide some restraint of curl warp deformation. Now, that restraint, anytime you restrain a pavement from doing what it wants to do, you induce a stress. So we need to be aware of that, but what it does do is improves our ride quality. So if we have dowel bars and tie bars across our joints, we tend to see less movement of those slabs, less curling and warping than we would otherwise see if they were not there, and therefore our ride quality should be higher. Our ride quality is also higher because the dowel bars prevent faulting from developing, and that also influences the IRI value or other ride quality value. Of course, it's important that if we're going to put in dowel bars, and we usually do want to put in dowel bars, as Eric said, if we have any reasonable amount of truck traffic at all, then they need to last for as long as the pavement is designed to last for. That implies a certain degree of corrosion resistance or durability there. So 20 to 35 years for typical conventional pavements and repairs. And if you're doing long life, long service life, then the dowel needs to last as long as the life of the pavement, which could be as much as 100 years. I think Caltrans is talking about doing 100-year pavement designs. So in terms of an illustration of the deflection effects, we can look at an interior deflection, D sub I, meaning the deflection of the interior of the slab. On the left-hand side, we have an undoweled transverse joint situation. And we can see that at the corner, if we don't have dowel bars, we have a free edge at the outside lane there, and we have a undoweled joint we may have as much as 5 times the deflection of the interior of the slab at that corner location. The interior corner, where we've got some aggregate interlock both along the transverse and longitudinal joints, is still 3 times as high, approximately 3 times as high as the center slab deflection. If we go to a doweled joint condition, the outside corner still higher than the center, but we've reduced it by about 60% from the undoweled condition. And similarly, the interior corner condition, instead of being 3 times the interior, is now only 2 times the interior. So dowels are very effective in reducing those deflections. Often talk about deflection load transfer or relative deflection of joints as measures of joint efficiency, of how effective our joint load transfer system is. These are 2 different competing concepts. Load transfer efficiency, which is based on deflections commonly, the ratio of the unloaded side of the, if you load one side of the joint, it's the ratio of the deflection on the unloaded side divided by the deflection on the loaded side multiplied by 100. That's one of the more common definitions. There are other definitions as well. Relative deflection looks at simply the difference in deflection between the loaded and unloaded sides. I believe that that is a more accurate approach, and we're seeing a movement towards using that relative to load transfer efficiency. It's a deficient concept, but it's load transfer efficiency. Don't really have time to get into that here, but I think this is where we're going to relative deflection. We've got a long history of using LTE, which ranges from 0 to 100%. If we have no deflection of the unloaded side relative to the deflected side, that's 0% load transfer efficiency. If both sides deflect by exactly the same amount, that would be 100% load transfer efficiency and a 0 relative deflection value. Typical dowel bars that we would use in the US here, typically 18 inches long for new construction. They may be a bit shorter in repairs and retrofits. Obviously, if we do brand new construction of the pavement, like you see in the top photograph here, there's going to be some potential variance in where that saw cut goes above that dowel bar. There's a certain minimum amount of embedment that we'd like to see on each side of the joint. And so the dowel is a little longer than we really need it to be from a structural standpoint at 18 inches, but that's to account for the fact that the sawyer may cut the joint an inch or 2 or 3 even, one side or the other of the middle of the basket. Perhaps the basket wasn't marked properly or whatever. When we have a dowel bar retrofit or a repair, we know exactly where the joint is relative to the midpoint of that dowel bar. So we see a lot of folks using shorter dowel bars. 12-inch bars, 14-inch bars are fairly common. I'd point out that Minnesota is one state uses 15-inch bars routinely for all their construction. Typical diameter, around 1 inch to 1.5 inches on roadway pavements, 1.5 to 2 inches for airports. How big that diameter is really varies more with the loads that you expect to see on it, as well as the spacing of the dowel bars and the shape of the bars. And now that we've got FRP bars, also depends on the material that you have in place there. Historically, we've done things since the 1950s in this country saying that the dowel bar diameter needed to be 1/8 the thickness of the concrete. We've learned that's not necessarily a good idea. We've gone to slightly larger bars on our thinner pavements. But again, I would say that if you had, for example, a tubular bar where you've got a lighter structural section, you need a slightly larger bar to have the same performance as you would have with a solid bar. The same thing is true for FRP bars, fiber reinforced plastic or polymer bars, where the material is, the elastic modulus of that material is much lower than that of steel. So you need to have a little bit bigger bar if you want to have the same behavior of the joint. Corrosion protection needs depend upon where you're at, obviously, and there's a lot of different types of corrosion protection schemes. Barrier protection, where you just have a coating of some sort, whether it's epoxy or plastic, or even one dowel manufacturer makes a steel bar with an FRP coating on the outside. There are some passive cathodic coatings with zinc, both galvanized and zinc alloy strip. Then, of course, there are non-corroding materials such as stainless steel, microcomposite alloys, and solid FRP bars. Optimized dowel spacing. We used to use dowels every 12 inches all the way across the joint. If you had a 12-foot lane, you'd have 12 bars there. We're seeing a trend now towards what we'd call more optimized or more idealistic dowel spacings, putting the dowels where they are needed and also avoiding things that we know have caused problems in the past. And this is why we're starting to see the use of more like 11 bars in a 12-foot lane, so that we've got 1 foot clear between the outside bar and the outside of the paving shoe. So what we found in the past is if we have that outside bar too close to the edge, sometimes the paving shoe will catch that bar and it may drag the basket, and then we've got a misalignment problem. And also if the bar gets too close to the edge and that bar carries a significant load, it might actually even cause a little bit of spalling right at the edge. So moving that bar in a little bit, it's been found to be very helpful. We're seeing that taken to an even greater extreme by putting the bars where they're needed in the wheel paths. You see a picture here from the Illinois toll road with 5 bars per wheel path. Utah, for example, uses 4 bars per wheel path routinely. And the bottom photograph here is a picture of a 2-lane road in Minnesota where they did a dowel bar retrofit and they put only 3 bars in the outside wheel path only. And that is a photograph there of a project that's more than 20 years old and performing very, very well with just those bars in the outside wheel path. You can evaluate these different spacings using DowelCAD software. And this is another one that's available for free at the apps.acpa.org website that Eric was talking about previously. It will allow you to compare conventional configurations with alternative configurations and look at the impacts those have on dowel bearing stress and corner stresses in the pavement and so on and so forth. So a way to make the pavement more efficient using a little less steel, make it cost a little less, and still have very, very good performance. In addition to having optimized dowel layouts, we also have some optimized dowel designs, with the object of the game being to try to reduce the contact stress or the bearing stress between the dowel bar and the concrete. If that bearing stress between the dowel and the concrete is too high, then the concrete that supports the dowel bar can degrade over time, and the dowel bar loses its effectiveness because it becomes loose within the pavement, and then you have higher deflections again. So some of the examples we're seeing now, we've seen elliptical dowel bars where you have a dowel that's kind of an oval shape and it's a little bit flatter on the bottom than it is, it's a little wider than it is tall, let's say. Taken to an extreme, we have plate dowels, which we see used extensively in industrial paving, indoor warehouse applications where they have relatively thin pavements and they want a thinner dowel bar. Then we see tubular dowels like the ones you see on the right-hand side here. These are tubular stainless steel, but there are a number of other tubular designs as well, epoxy coated over zinc, just plain old epoxy coated steel tubes. And these give you, again, much less weight, more effective use of the material, slightly larger diameter to achieve the required stiffness though. A lot more information on all these topics. Again, as Eric pointed out, this is kind of a Reader's Digest abridged presentation of a 1-day or day and a half training course that we've done in the past. But one of the documents that has a lot of information on dowel load transfer system design and analysis is what you see here from the National Concrete Pavement Technology Center, and the link for a free download is at the bottom of the screen. Let's talk a little bit about tie bar system design. And Eric talked a little bit about this earlier. We use tie bars, again, an important structural element. Their main purpose is to hold the joints tight. They can assist in providing load transfer through keyways and aggregate interlock. And in doing so, they assist the keyways and the aggregate interlock in providing the load transfer that's necessary for sharing the load across the joints. It's not my opinion that unless you use very, very large tie bars with comparable diameter and spacing to what you have for your dowel bars, they really are not providing a great deal of direct load transfer. But that's okay because we use dowel bars across transverse joints because that's where every wheel load crosses a transverse joint. We don't typically see a lot of wheel loads running right down the longitudinal joint. Obviously, there's a few now and then as a truck passes from one lane to the next, but typically our wheels are running, 1.5 feet, 2 feet away from those longitudinal joints, and we don't need the tie bar to serve as a load transfer device. If it did, you would have very, very high bearing stresses because the typical diameter on these bars is much, much smaller than what we have in dowel bars. They also provide some restraint, a little bit of restraint of curl warp deformation, but again, these bars are not terribly stiff. They're not going to greatly reinforce that joint from rotating. An alternative, and Eric mentioned this in his presentation, I'll throw it in here, is a corrugated or sinusoidal keyway. We have not seen this adopted much in the United States. Pennsylvania, I think, has a trial section either planned or recently constructed. This is a practice that has been in place for many years in Australia. If you want some more details on that, I think I saw that George Vorobiev from Australia is on this call here. He could probably add additional information on this, but this is a plate right out of their standard specifications showing kind of how that is formed. And you've got an irregular surface there. It doesn't have the single large section of concrete to break off like we would have in a normal keyway that we've seen in thin pavements. And you can see a photograph of it down here on the right-hand side and on the bottom. You can kind of see the corrugations and the tie bar there. Because again, without that tie bar there to hold the concrete tight across that joint, then those interlocking keyway fingers really can't become fully effective. When we come to tie bar design, a lot of states have unfortunately gone to a system with one size fits all, and one size does not fit all. And we've seen some problems, some performance problems from using a standard design that might be, for example, number 5 bars at 30 inches everywhere. There are certain situations where number 5 bars at 30 inches works. But if you have, for example, a relatively thin concrete overlay placed on an unbonded overlay, so it's placed on geotextile fabric, where there's very little friction in the underlying interface, that's a very different amount of force that goes across that joint than if you have, for example, a 13 or 14 inch pavement on top of a cement stabilized base, and it may be bonding or interlocking with that base, and there's a lot more force taking place. So you need to have different designs for these different situations. And you can see a photograph here of a crack running down along this the center of this lane here. And what happened was that they have a very short distance to the outside edge, and they used the same tie bar design across that joint there, and they actually ended up reinforcing that joint. And instead of that joint activating, concrete wanted to crack someplace, and it was easier for it to crack along the ends of the tie bars than it was for it to crack down that joint itself. So we can and occasionally do over reinforce our longitudinal joints. So there are design procedures that are easily available. I know we like to try to make things simple for design and construction, but this is a place where we need to take a little bit more effort. I mean, even as early as the 1986, 1993 AASHTO design guides, if you're still looking at and using those on occasion, based on subgrade drag theory, the old theory that you need to have enough steel in the joint to offset the friction between the slab and the subbase based on the distance to the nearest free edge. That's what this is. The area of steel is equal to the tensile force developed, that's T, divided by the allowable working stress in the steel. And there's an equation for it. It's a pretty simple equation based on the distance between the working joint and the pavement edge, the slab thickness, the unit weight of the concrete, and a frictional coefficient. But we even have nomographs for certain situations, and you can develop your own nomographs pretty easily based on the grade of the steel, the assumed subgrade friction factor, and the diameter of the tie bar. So you'd simply come in with the distance to the free edge, you go up to the thickness of the slab, and you come off to the side, and it tells you what the tie bar spacing is in inches for that particular set of conditions in that particular grade of steel. If you want to get more complicated about it, or more sophisticated, let's say, then there is the mechanistic empirical tie bar design approach. This was developed by Applied Research Associates, I believe, for the Portland Cement Association back in the last decade, 2 decades ago now, I guess, 2009. Takes into account where you are, the type of cement you're using, the cementitious materials content of your mixture, the coefficient of thermal expansion, the thickness of your slab, your lane configurations, how many lanes you're tying together, what type of a base you're on, when you build it, how you cure it, and then it calculates out a recommended tie bar size and spacing and grade of steel, taking into account not only the subgrade drag, but also curling and warping and other sorts of environmental factors. So, and this is another one of those things that is available for free online at the apps.acpa.org website, this tie bar design calculator. Okay. One of the last topics I want to cover here is dowel bar alignment and location requirements. And again, we could spend quite a bit of time talking about this. We're just going to touch on it. If you have further questions, you want to dig down into this, we can go through that in the question and answer part. But there are several different components to dowel bar positioning. There's the alignment, which deals with rotational movements or rotational displacements of the dowel bar, and we can rotate it both horizontally in the horizontal plane, which we call skew, and we can rotate the bar vertically, which we call tilt. And we got three different positioning errors: horizontal translation, where the bar is to one side or the other. It's centered properly on the joint, but it's not properly located with respect to the edge of the pavement. Longitudinal translation, where the bar is displaced with respect to the direction of paving, so it's not centered on the joint. And again, that can come from either misplacing the bar or from sawing the joint in the wrong location. Then we have vertical translation, where the bar is a little higher or a little lower than was originally intended. And the table above here shows the types of potential issues that you can have. All of these have the potential to impact load transfer. Rotational alignment will restrain the movement of the joint, or the opening and closing of the joint, so those have the potential to induce both spalling and cracking. And vertical translation usually has a potential only for spalling, but not really for cracking, in addition to the loss of load transfer. Again, I'm not going to go into this here, but ACPA did put out a very detailed dowel alignment and location guide specification about a year and a half ago, and it goes into providing updated guidance on calculating joint score, which is a means of assessing the potential for a joint to be restrained by dowel bar rotation, depending upon how many bars are rotated and how many of them, how badly they're rotated. It has guidance on procedures for measuring dowel bar alignment. You know, how many joints do you measure? How often do you do it for quality control purposes? It establishes guidance on acceptance and rejection criteria, noting that those are different. There's a target that you want to see, and you may not achieve that, but it may still be not to the point where you would actually reject it. You may have a pay factor adjustment or something, but there's certainly some point at which the bar is sufficiently mispositioned to cause you to reject that joint. You need to remove and replace. It also provides guidance on percent within limits based pay factors based on experience from states and provinces in Canada. So I would direct you in that direction for more information on dowel positioning information. In terms of dowel and joint construction, we can talk about placing the steel. And if we have pre-placed steel in baskets and on chairs, we want to make sure that they are anchored properly. And there is, again, guidance out there. This is an FHWA tech brief, was written with the assistance from, or really the main authorship from, the American Concrete Pavement Association. Jerry Voigt and Eric Ferrebee, I believe, both worked on this. And FHWA put their stamp of approval on it. And it provides a lot of guidance in terms of where to put the anchors, the types of anchors that you need to use for different types of bases, and how many, where they need to be, which side of the baskets. Do you anchor the top bar, the bottom bar of the baskets? So all that information is in here, but it's very important, obviously, if we're going to place these things on baskets, that they stay in place as the paver moves across. And this becomes particularly important now that we are often using a little stiffer mixes, a little bit more rocky mixes, optimized mixes that have a little more aggregate in them and a little less cement. So that the anchoring becomes very important. One of the things that comes up very often, we see issues with dowel bar, tie bar interference. And if you do have a tie bar which is placed too close to a transverse joint, or even within the transverse joint, God forbid, it will interfere with the joint opening and closing, and you will get things like you see in this bottom picture here, where you get spalls at those interior corners, where there's interference, sufficient interference that the slab wants to shrink in two directions, but it can't do it because it's restrained in both directions by the placement of those bars. So what we often will see done is that you'll skip a bar, a tie bar. As you can see in this operation, this is a dowel bar inserter behind this paver, and you can see they've got 4 tie bars in a row. Then they skipped one. That's where the dowels are going to be implanted. Most states have adopted a guidance of holding the tie bars at least 15 inches from the transverse joints. That puts you 6 inches off, at least 6 inches off the ends of an 18-inch long tie bar, 18-inch long dowel bar. And a lot of states have gone to using 30-inch distances to the joint, which puts you 21 inches off the end of a half of a 18-inch long bar. In fact, the Federal Highway Administration Technical Advisory 5040.30, which was just released last year, says specifically tie bars should not be placed within 6 inches of the ends of transverse joint dowels, i.e. within 15 inches of the transverse joints, to avoid corners falling and other potential interference effects. And it goes on to say you might need to modify your tie bar spacing to get the right number of bars to hold the joints tight, but still avoid conflicts with the joint dowels. When we have inserter placed seal, we still need to maintain those distances. You can see here dowel bars being inserted vertically in the lower right-hand corner, and then we have a number of different schemes for inserting tie bars. This is a Gunnert and Zimmerman tie bar inserter, which does a vertical insertion. There's a Gomeco tie bar, which does a sidebar inserter, which is a horizontal lateral injection of the bar into the side, right behind the paving pan. And this is one that is kind of a rotational thing. You can see the bars in a magazine here, and it picks up the bar and it rotates down, and on a particular spacing, drops them into the pavement. And again, if you're going to you'd have someone sitting here and putting those into those wheels, you would make sure that at the appropriate times you would leave one out as you're getting too close to that dowel basket. No matter what you do, you've got to know where the joint, where the dowel bars are, so that the sawing is done at the right location. That should be fairly easily done with pre-placed steel. Once the dowel bar basket is in place, simply placing a wide paint mark out to the side, or a nail and a washer out to the side, like you can see in the top right-hand photo here, so that after the pavement has been placed, those points are easily identified, and a straight line can be pulled across the pavement and marked into the pavement surface with a chain drag, or simply used as sighting points for the saw operator. In terms of the sawing of the joint, we need to do it in a timely fashion. If we get on there too early, we see raveling of the joints. And if we get on too late, we may see cracking, uncontrolled cracking. So there's a time in between there. And unfortunately, that window that we have available to us varies with a lot of different factors. If we have changes in the weather, sudden temperature drops can result in very rapid cooling and shrinkage at the top, which can cause a crack to form. Or sudden temperature rises can cause the pavement to dry very rapidly. We'll get plastic shrinkage cracking. High winds, low humidity, same sorts of thing. Subgrade subbase type, if you got a lot of friction, that increases the rate at which these stresses will develop and will reduce the amount of time available for sawing your joints. Stabilized subbases, you get the higher friction or interlock as well. Different mixture types, whether it's a high water demand mix, got a lot of recycled aggregate, for example, in it, or if it's a rapid early strength mix with a lot of hot cement. All these different sorts of factors can influence the sawing window. Again, there is a tech brief on this. ACPA has a tech brief called Early Cracking of Concrete Pavement Causes and Repairs. Again, available free from your local chapter, from FCPA and from ACPA National. There's also the integrated manual for concrete pavement construction that's put out by the CP Tech Center. And I've got a source for that coming up in one of the later slides. Illustrations of what you can get. Too early, you get a lot of raveling. Too late, unfortunately, too late looks just like really good. And you may not know that it's too late until it's too late. But getting guidance on what that window is can be gained by using a program called HyperPave. Again, available free of charge for download. It's developed by Transtech Group under a contract with Federal Highway Administration. Software is free. You can get it at hyperpave.com, or it's also available on the apps.acpa.org website. And you may not know that it's too late. When you cut that, it looks like a good joint, but after the fact, you may find that you have a meandering crack that wanders along, very often off the ends of the tie bars, indicating that it was not able to perhaps open on time, or that perhaps the depth of the cut was insufficient. Because again, when we do put tie bars across the joint, we are reinforcing that joint. So we have to make sure that we cut the joint deeply enough that that location is still the weakest plane in the concrete panel, even though there are reinforcing bars go across it. And this is why we need to have deeper saw cuts in our longitudinal joints. Typically, minimum of 1/3 the slab thickness. You don't want to get down and nick the bars, but you need to be at least 1/3 the slab thickness. Transverse joints, a minimum of 1/4 the slab thickness if we're on a granular base, and a minimum again of 1/3 the slab thickness to control it when we're on a stabilized base. We may get by with thinner saw cuts if you're using an early entry saw. Might be as little as 1.25 inches in depth, but if you start to see dust coming out of it, suggesting that the slab is dried out, you might want to revert back to a saw cut depth of T/4 in those cases. If we do it right though, with the right location, the right time, and the right depth, the joint will activate at the right location over the centers of the dowel bars.